In Chapter 3, we will be covering acids and bases, and if you recall, acids and bases are about proton transfers back and forth. So if you will recall, an acid is a proton donor, which means that the base is a proton acceptor. In the case of HCl and water, HCl is the acid, and water is the base. So HCl is donating the proton, the base is accepting the proton. So if that transaction happens, so we end up with Cl- and H3O+. So a conjugate acid results when a base accepts a proton, and a conjugate base results when an acid gives up a proton. So if we look at in reverse, this is the conjugate base. So that was what resulted when the acid gave up its proton. This is the conjugate acid, which resulted when the base accepted a proton. So if you were driving the equilibrium backwards, this is the acid because it's going to donate the proton to the Cl, and this is the base. So if we look at the product here, this is the base. This is the acid. That proton is going to get donated. So we get an H here, and then this O becomes an OH minus. So this would be the conjugate acid. This is the conjugate base. If we look at the flow of electron density, that will help us to understand what is going on here. So the base is negatively charged. So there's this negative charge here, and the hydrogen is partially positive, and they're attracted to each other. So that base really wants to give the hydrogen a lovely hug before the hydrogen leaves the acid. So this pair of electrons will go on to the A, and you get the BH and then A minus. When the bonds break and form, the pairs of electrons move, and then again we can show their movement with the curved arrows. And you can think of it as a fishing rod. So you have your fishing rod here, which is the base, and it's going to grab one of these protons or the fish, and then it will just hook into that and then pull it away from the school or the acid. So this is the H, this would be the acid. So the curved arrows are showing the reaction mechanism. And learning to draw these mechanisms with the arrows and pushing those electrons around is going to be one of the most valuable skills in this class. If you can master that and have a good understanding of the mechanism arrows, it will get you very far in this class and you won't have to memorize as much. Okay, so the acid can't lose its proton without the base taking it, and all acid-base reactions happen in one step. The mechanism shows two arrows indicating that two pairs of electrons move simultaneously. So this double arrowhead here is telling us that there's two electrons moving at one time. If we draw a mechanism for the following acid-base reaction, we're going to label the acid-base, conjugate acid, and conjugate base. First thing we want to do is identify the acid and the base. The base is usually negatively charged, so I'm going to go with that one for the base. And so water has to be the acid. And usually the base, which is the negative, is going to be the fisherman looking for the hook that's going to grab a hydrogen. So these electron arrows will go here. It's going to grab that hydrogen, and then the electrons from the hydrogen, it can't stay with it, so it's going to give it to the oxygen. So now this oxygen has this extra lone pair, and the hydrogen has gone to the O minus to make the H here. So the acid is what is donating the proton, the base is accepting it. So in reverse, this is the conjugate base, and this is the conjugate acid. Drawing the mechanism for this one, label the acid base, conjugate base. So you can draw it in any order. I'm going to start with labeling just the acid and the base. Here we have an O minus and an HCl. This is the acid. This is the base. Our fisherman person is going to come out and grab the hydrogen with its hook. These electrons go on to the chlorine, Now we have the carboxylic acid here and then the Cl minus. So this is the conjugate acid. This is the conjugate base. So this is just a transaction of swapping protons around. So to determine if a proton transfer reaction will occur, you can use two methods. The first one you can use is the quantitative method, which requires you to memorize and compare pKa values, or you can use a qualitative approach, which is analyzing or recognizing patterns of the acids. So the Ka is the equilibrium constant for the reaction between an acid and water. So it's kind of like asking how likely is it to give up a proton. So the expression is Ha plus H2O gives us A minus and H3O plus in equilibrium. And you have the Ka, which is the products over reactants, and then the pK, which is the negative log of the Ka. So a lower pKa equals a stronger acid. So if you have a pKa that is less than 0, that means the Ka is greater than 1, so it's completely dissociating into H2O. So if you have acids with a pKa less than 0, those are usually inorganic acids like Hi, HCl, HBr. So we know these are very acidic. There's lots of pKa's that you can memorize, and you should know some of them so that you can ballpark things. So you don't want to confuse pKa with pH. For example, the pH of water is around 7, but the pKa is 15.7. Things that have higher pKa's are weaker acid. Strongest acids have the low pKa's, which are negative. So H2SO4 has a pKa of -9. Don't confuse pK with pH. pH is a measure of the acidity of an aqueous solution or the concentration of H+, while pKa is the measure of the ability of a particular compound to donate its proton. So the ones that you should become familiar with, i.e. memorize, are carboxylic acid. You want to know the pKa of water, which I've already asterisked here, of a general alcohol, a proton next to a carbonyl, an alkyne proton, alkene proton, and an alkane proton. So if you have these couple of ones memorized, you can use them as a frame of reference for other problems that we end up doing. For the following pair of compounds, identify the more acidic compound. Right now, all you can do is compare the values from the table. So we're looking at pKa's of an NH3 and one of a proton next to a carbonyl. So I'm going to go back to this table here. We have an NH3 here, so that's around 38. And the proton next to a carbonyl, there's two kinds here. There's the one that I asked you to learn, which is around 19.2. But there's this other one that is between two carbonyls, and that one is around 9. So this one, pKa is around 38. This one was around 9. So the more acidic compound will have a lower pKa. So that will be that guy right there. Okay, if you need to quantitatively compare bases, you can do the same thing, but it's the opposite trend of acids. So strongest acids equals the weakest conjugate base, and the weakest acid equals the strongest conjugate base. So the pKa's have not changed, we just are observing a different trend. So weakest acid equals strongest base, and then strongest acid equals the weakest base. So based on that, which is the stronger base? So what you can do is first draw the conjugate acid of each base. So this is the conjugate acid. Then you can compare the pKa values. This is the one that we just looked at in the last slide. So this pKa was around 9, and this one was around 19. So this one would be a stronger acid, which means that it will be the weaker base. So that one right there would be the stronger base. If we know the pKa values, we can predict which direction of the equilibrium is favored in the acid-base reaction. For the first reaction here, we have a base plus acid, conjugate base. And when you're trying to predict the equilibrium based on pKa's, you need to compare the acids. So we're going to look at this acid and this conjugate acid. So the pKa of water is around 15.7, and the pKa of an alcohol is around 18. So the lower pKa means stronger acid, which means it will dissociate more readily. So that means that 15.7, the protons will come off here more easily than 18. This is the higher one. So when you're predicting the equilibrium, you want to favor the side that has the higher pKa. So this side is favored because the higher pKa means that it is less likely to dissociate. For the next example, we're going to compare acids again. The pKa of water is the same, so that's 15.7. For an alkane, that was around 50. So this one is very favored, which is why the arrow here is in favoring the products. So you're looking for the higher pKa, so this side is favored. It's not really much of an equilibrium, it's just the reaction that happens. If you're going to look at things qualitatively, we can compare structural ability to determine which is the stronger acid. What is the way to do this? You want to compare the stability of the conjugate base. Remember, if you're looking at things quantitatively, with the pKa's you're comparing the acids, but if you're going to look at it qualitatively, we're going to compare the bases and the conjugate base. If A minus is very stable or a weak base, then HA has to be a strong acid. And if, on the other hand, A minus is very unstable, then HA must be a weak acid. So the equilibrium favors the side with the more stable anion. If you want to look at factors affecting the stability of the negative charge, we use the acronym ARIO. So it's atom, resonance, induction, and orbital. Which atom stabilizes the charge better? We're going to look at butane versus propanol. So to compare the atoms, we're actually comparing the carbon that's holding the hydrogen versus the oxygen that's holding the hydrogen. So draw the conjugate base. So the conjugate base is what results if the hydrogen is plucked off. So we'd have a C minus here, and then an O minus. And then you want to look at the electronegativity of the atom. And which one is more electronegative? That means that it's better at stabilizing the negative charge. So oxygen is more electronegative than carbon. So that one will be better at stabilizing the negative charge versus carbon. If it's better at stabilizing the negative charge, that side is favored. So oxygen's more electronegative, so it's better at stabilizing the negative charge. So if we're looking at stabilization, we have the both of them lifting that negative charge. Oxygen can do it better because it's more electronegative to start with. So it is happier holding that negative charge over the carbon. We can also look at atoms in terms of their size. Electronegativity and size can stabilize a negative charge. So now we're comparing oxygen to sulfur. Those are both in the same column, so they're both pretty electronegative, even though oxygen is slightly more electronegative because of its location, but that is less important. So here we're going to draw again the conjugate base. One thing you do want to look at is the size. Oxygen is smaller than sulfur. So if we're trying to distribute a negative charge over an atom, it's better distributed over a large surface area than a small one. So sulfur is going to better stabilize that negative charge over a larger area. So between these, which can stabilize better, that one is going to be the sulfur because of its size. We can also look at resonance, which can greatly stabilize a formal negative charge. And what it does is it spreads out into partial charges. So what we can do is draw first the conjugate bases. So in the first case here, this oxygen is carrying the negative charge only on the oxygen because it can't share it. We can't draw any resonance structures. Oxygen only can carry the negative charge, so this is called localized. The negative charge is on the oxygen only. In this case, we have an sp2 carbon and another oxygen atom. So this electron pair can come in here, and we can draw resonance structures where electrons go onto the oxygen. We can draw resonance here. And it's spread out over the 3 atoms. And that is delocalizing it. You have resonance structures, they can share the load. The negative charge can be shared over 3 atoms instead of the one of the oxygen, so this can stabilize it better. So induction is another way that we can use to measure how acidic something is. So that's going to stabilize by withdrawing electron density from the site of acidity through bonds. So it's kind of like playing tug of war. You're going to compare acetic acid with trichloroacetic acid. This acetic acid has just hydrogens. This one has electronegative chlorines that are on there. That's the only difference between those two. So if we draw the conjugate base, get the negative charge here. If you draw the dipole moments, this one isn't being stabilized anything, but here we have electron density being pulled out. You have these chlorines. This is the acidic proton. These are pulling electron density away from there versus just the acidic proton with the electron density here. So if you have this pulling electron density out, that makes it more acidic. And so these ones can stabilize the charge better because it's pulling electron density out through induction. So there's other things for induction that can affect the pKa's. One of them is the type of substituent on there. So if you have a more electronegative substituent like fluorine, that is 2.66 pKa versus acetic acid, which is 4.76. Bromine is less electronegative than fluorine, so that's 2.86. And then chlorine is 2.81. So the more electronegative an atom, the more it can pull electron density out of there. We can also take into effect the distance that the electronegative atom is. So if you're thinking of a tug of war, you're going to put the strongest person next to the middle, and that will have the most strong pull. So the Br next to the carboxylic acid is 2.97. We go a little bit further away, that drops to 4.01. Another carbon in between is 4.59. And then if it's really far away, it drops it to 4.71. So it can't pull very strongly from here because it's so far away. There's also additive effects. So again, this is 4.76. If we add 1 chlorine, the pKa drops to 2.81, and then adding 2 chlorines drops it even further. And the last one that we'll look at is orbitals. So the type of orbital can stabilize the charge differently by pulling electron density closer into the nucleus. So we have sp3, sp2, and sp. And if you look at the shape of the orbitals, this one has more s character. So it's 50% S, 50% P, which means it can hold the electron density closer. So the sp3 over here, the electrons are further away in the sp3 orbital, so it's not held as closely. These sp ones can hold it pretty closely. So if we're looking at the conjugate base of these, this one has the electrons held more closely because it is sp, so this one is more stable. So the sp is stronger at carrying that because it can hold the electron density closer to itself. Ethane has the pKa of 50, which is the sp3. Ethylene is around 44, and the sp is around 25.